In this lecture, we are going to talk about computation of the probability by conditioning. Obviously, one of such thing we have already done when we did probability theorem of total probability, and we will basically going to see now is some kind of extension of what we call the theorem of total probability. Okay, so theorem of total probability we have discussed in theorem 1.16. So if you forgot it, you just cross check it once again and then come back here to see this one. Okay, so you see that what we are trying to do is that we are basically trying to find out what is the probability x belongs to A, and we are trying to find this one using conditional probability conditioning using conditioning. How can I do that? Well, see that probability x belongs to A. We know that this can be written as expectation of the indicator random variable of the set A. Right? We have seen this one that expectation of IAX, where I is the indicator random variable, is nothing but probability x belongs to A. So, and on the other hand, if I try to find out expectation of IAX given y equals to y, this is nothing but the conditional probability that x belongs to A given y equals to y. So we are basically trying to do this one, and now you see that this expectation using the theorem to 3.23, we can write this expectation as expectation of IAX given y. Now, when y is discrete, as we have already pointed out, if y is discrete, this can be written as a summation form. When y is continuous, this can be written in terms of integration. Okay, so we have written this way. Now you see that what we have finally, we have that x belongs to A is nothing but, or probability of A, instead of x belongs to A, I'll write it probability of A. So probability of A can be written as summation y belongs to s of y, probability of A given y equals to y into probability of y equals to y, which is for y discrete, and when y is continuous, this probability of A can be written as minus infinity to plus infinity, probability of A given y equals to y into the marginal density function of y into dy. Okay, and you notice that this one, for when y is discrete, this is exactly the theorem of total probability. We can get this one using the theorem of total probability, because y equals to y, you just this set y equals to y, these events are disjoint for different values of y, and it is a countable that if I call by equals to y equals event y equals to y, then then the collection of by is actually a countable one. So that's why this expression I can get from the theorem of total probability, but obviously this is not, we cannot get this part from the theorem of total probability, and that's why you can see this result is a kind of extension of the theorem of total probability. Okay, so let us see some application of this result to compute different kind of probabilities. The first one is, suppose I have two random variables x and y, they are independent and they are continuous, and their marginal PDFs are fx and fy respectively. Suppose I try to find out what is the probability x is less than y. I can do it using this part very easily, because I will try to do the conditioning with respect to y. Y is a continuous random variable, so that this probability can be written as the integration of x less than y. The A is basically x less than y. So probability of A given y equals to y into the density function of y dy. Okay, so now because y equals to y is given, so small y can, this capital Y can be replaced with small y. Now this part do not involve any y, this part do not involve any x, so that's why these two parts are independent. So probability of x less than y given y equals to y is basically same as probability x is less than small y. Into the density function, this part is nothing but the cumulative distribution function of x. So we put this one, and so given the expression of fx and fy, small fx and small fy, I can find out the capital Fx from small fx, and then I can find the probability x is less than y from this integration. Okay, you can do the same thing with the condition that x equals to small x into the marginal density function of x. You can do the same way. Only thing is that now we'll have a one minus distribution function of y here, and the marginal probability density function of x here. Okay, so this you can write and you can check, but that if x and y are independent continuous random variables, then probability x is less than y can be found from this expression. Okay, so let us now use this example 3.23 in example 3.24. So example the 3.24, we have taken that x and y are IIDs. So that means both the density function are same, both the density function are same. So I can write now the probability x is less than y as the integration from minus infinity to plus infinity f of y into the density function of y dy. So and notice that this capital F is the distribution function corresponding to the small f. So that means that small f is the derivative of capital F. So from there you can easily do this integration and we can get that probability x is less than y equals to half. Similarly, now extend the role of y and x, I can get that probability y is less than x is also half. So that means probability y is less than x and x is less than y. Both the probability of both the events are half, and that shows that probability of x equals to y equals to 0, which we have already seen earlier also, that if x and y are continuous random variables and they are independent, then they will have a joint density function, and if they have a joint density function, then probability x equals to y is 0. Okay, that we have seen earlier also. It is here we have another proof for that thing. Okay, so okay, now let us consider another example. It is a little lengthy example but very interesting one. So what I am going to do here is that suppose I have two random variable x and y. We have assumed that x and y both are independent. We want to study the random variable z, which is x plus y. So basically what we want to study is that suppose x and y both are discrete, whether z will be discrete or continuous. X and y both are continuous, whether z will be discrete or continuous. One of them is discrete, another one is continuous, then whether z will be discrete or continuous. And obviously, in each case, depending on whether z is discrete or continuous, we try to find out the corresponding probability mass function or probability density function, whatever applicable for z. Okay, that's what basically we are going to discuss here. So we start with the simplest case, that when x and y both are discrete random. So we know that if x and y are both are discrete random variables, then x comma y as a vector is also a discrete random vector. And for the discrete random vector, this result we already have, that if you have any function of a discrete random vector, that will be a discrete random vector. Okay, that will be either discrete random variable or discrete random vector based on whether the codomain of the function is r or r to the power n. So in this case, x plus y, so codomain is a r. So in this case, obviously z, which is equals to x plus y, will be a discrete random variable. And I can find out the density probability mass function of z very easily, because probability mass function of z, which is basically probability that x plus y equals to z. I do the condition with respect to y. You can do the condition with respect to x. The final expression will be a little bit different, but yeah, you can get almost the same thing. But here, for example, I start with the conditioning with respect to y. Then the standard thing we did, that this y is replaced by small y. And so I have that the first part turns out to be probability that x equals to z minus y, because x and y are independent, and then the probability mass function of y. So finally we got that it is the probability that z equals to z or x plus y equals to z can be written as summation y belongs to sy, f of x at the point z minus y into f of y at the point y. So it is very easy to remember, because when y equals to y, x has to take the value z minus y, and because they are independent, the product will come. Okay, you can remember this way, but obviously that mathematical computation is basically need to do in this particular manner. Okay, now so that means basically in this case, when x and y both are discrete, the z is also discrete, and probability mass function of z is given by this expression. Okay. Now let us consider the second case when x and y both continuous. Now when x and y both continuous, first what we are going to do is that we are going to find out the cumulative distribution function of z. Okay, because in this case obviously I do not know whether z will be continuous or discrete, but we know that the cumulative distribution function going to exist always. So first we will try to find out the CDF of z, and from that we try to check if z is continuous or if z is discrete. So cumulative distribution function of z, by definition x plus y less than equals to z. Use the conditional formula, condition with respect to y. So it turns out to be integration from minus infinity to plus infinity, probability that x plus y less than equals to z given y equals to y into the density function of marginal density function of y dx. Again do the same thing, put y has null y here, and now these two parts are independent, so that conditioning I can remove. So I get this one. Now this part is nothing but the cumulative distribution function of x. This part is nothing but the cumulative distribution function of x. So this one can be written as the integration of the marginal density function of x. Okay, so I can write that probability x is less than equal to z minus y as the integration from minus infinity to z minus y of the marginal density function of x dx. Right. So now what I am going to do is that I am just going to do a change of variable, and what I am going to take is that x prime equals to x plus 1. So if I make this transformation from x to x prime, in the first integral, we get that the integration range of the integration changes to minus infinity to z here, and instead of x I have x prime minus 1 and then dx prime. Now take this integration outside, because everything is positive non-negative here. I can interchange the order of the integration. Take the inside integration outside that I have taken here, this outside integration taken inside, and I can write then this expression in this manner, and you see that the inside quantity of the curly bracket. So what I have, the inside quantity of the curly bracket is basically a function in x prime, because when I do the integration with respect to y, it is a function in x prime. So suppose this function is called g. So that means basically the cumulative distribution function of z can be written as the integration from minus infinity to z small g of x prime dx prime, where small g is nothing but this quantity. That means small g, that means basically that z is a continuous random variable, and the PDF of z is given by this expression. Okay, so PDF of z, which is x plus y, is given by this expression at the point z, which is given by this expression. And again, it is not very difficult to remember because y is continuous, so I need to do the integration, and then basically y takes value y, and in that case x will take value z minus 1. Okay, it's not, not mathematically correct statement, but it is this way it is always easy to remember. Okay, you can just think it is not the probability, density function is not the probability, but sometimes if you think density function as a probability, it is very easy to remember. But remembering this thing is easy, but obviously I can again want to emphasize that density function is not. Okay, so so in case of both of the random variable x and y are continuous random variable, we have shown that x plus y is continuous random variable, and the probability density function of x plus y is given by this expression. And this one sometimes called the convolution of two density function, convolution of the density function small fx and small fy. Well, again, you are changing the role of x and y. That means basically instead of conditioning with respect to y, if you condition with respect to x, you will get that the joint density function of z can be written in this particular form. So these two are equivalent expression. These two are equivalent expression. Okay. Now let us consider the case when x is continuous and y is discrete. So last case we are now going to consider that x is continuous and y is discrete. I first try to find out the cumulative distribution function because I do not know whether z will be continuous or z will be discrete or none of them. So I start with x plus y is less than equals to z. Again, I do the same conditioning, conditioning with respect to the discrete one. It is always easy to do the conditioning with respect to discrete one. If you do the conditioning with respect to continuous one, the computation becomes little complicated. Okay. So again, the standard thing, put y equals to small capital Y instead of capital Y, put small y. Then the both the part will be disjoint. Remove them. So I remove the conditioning part. I have probability x is less than equals to z minus y. Okay. So now because x is continuous, that can be written in terms of the integration. And then again, I do the change of variable, same change of variable. So the integration becomes equal. Now I take the integration outside, summation inside. Again, that is possible because everything is non-negative here. All the functions are non-negative here. And again, we see that the cumulative distribution function of z can be written in this form, and that means that z again is a continuous random variable having the probability density function given by this expression. Okay, so if x is one of the random variable is continuous, another is discrete, sum will be continuous. Sometimes intuitively it seems that maybe if one of them is continuous, another is discrete, the sum will be discrete, but that intuition is not true. Okay, that intuition is not true. If this intuition works in your mind, take it from here that this intuition is not true. So what we get, finally we get that if x and y both are discrete, then x plus y is discrete. If one of x and y is continuous, then x plus y is continuous. If at least one of them is continuous, then x plus y is continuous. And all the cases we can find out the probability density function or probability mass function, whatever applicable, of x plus y from the density function or probability mass function of x and y individually. Okay, so let us just see one more definition. So still now we talk about conditional expectation for some event like x equals to x or y equals to y. Okay, so sometimes we need to find out the expectation for more complicated events like xy belongs to a. It may not be a singleton one. It may be xy belongs to a kind of a thing. A may be not a singleton one. So in this case, I can the formula is basically given by this, that I need to find out the expectation of h xy into I a xy. So basically, this conditional expectation is basically nothing but I try to find out what is the expectation inside a, inside the set A, because xy belongs to set A, that condition is given to me. So I try to find out the expectation inside the set A. Now that means that when I compute the expectation, h function, the contribution of the h function outside the set A should be 0, and that we can do by multiplying using the indicator function of the set A. Okay, so if you see now this whole product, that will be 0 outside the set A, and that will be h value of that will be same as the value of the h function. The value of the product is same as the value of the h function inside the set A. Okay, so I need to find out this expectation, and now I need to scale it. Because now I only want to find out the expectation inside the set A, so I need to scale it with the probability that xy belongs to A. So expectation of h xy given xy belongs to A can be computed as expectation of h xy multiplied by I a xy divided by probability xy belongs to A. Let us say some simple example. Suppose x follows a exponential random variable exponential 1. I try to find out this expectation. Okay, I try to find out this expectation. So using this one, well, in this case I have two random variable, but it is much easier one. I have only one random variable, so it is using this one, basically nothing but expectation of x into the integrator function of the set that x greater than 2 divided by probability x greater than 2. And now the rest of the thing we can do very easily, because this is a function of x. I know the density function of x, so that means integration will be this multiplied by e to the power minus x dx, and divided by this probability is nothing but the integration of the density function over the range 2 to infinity. And then you can do this integration and you have that result is 3. Okay, let us see another example. Suppose xy is uniform and I try to find out what is the expectation of x given x plus y greater than 1. Well, again I use the formula directly. I use the formula directly that it is basically x. Each function is x and multiplied by the indicator random variable of the set 1 to infinity divided by probability x plus y greater than 1. Now I know this is a unit on unit square. This is uniform, so I know the density function is basically 1 inside the unit square. Outside that it is 0. Outside that it is 0. So from that I can write that this expectation is nothing but double integration x dx dy, and this integration will only have a contribution inside the unit square where x plus y greater than 1. Okay, inside the unit square where x plus y greater than 1, that's why the range of the integration becomes this, and this integration is again integration of the density function over the range x plus y greater than 1. So from that we can write this two parts, and finally I have the expectation is 2 by 3. Clear? So this way I can find out those things. Okay, let us see another example of finding out this thing, that suppose a rod of length L is broken into two parts, then the expected length of the shorter part is. So suppose I try to find out the expected length of the shorter part. Now when I divide a rod of length L into two parts, then the shorter part will have the length less than equals to L by 2, right? So that means I need to find out the expectation of x where x is less than L by 2. Here this formulation is okay. As I said that if I break a rod of length L into two parts, then the shorter part has to have the length less than L by 2. So that means the expected length of the shorter part is basically mean that I try to find out the expectation of x given that x is less than L by 2. And what is the distribution of L? The distribution of L is uniform 0 to L because I can break in any point. So the density function will be same on all the points inside the interval 0 to L, and uniform is such density. So now the rest of the computation is quite simple, and it turns out to be L by 4. Another way of formulating it is nothing but, well, if I divide into two parts, and suppose the one part is x, then the another part is L minus x. So the shorter part is basically minimum of x and L minus x. So I can find out the expectation of this. Try to find out it and check that whether you are getting it is L by 4 or not. Okay, with that I stop for this lecture, and the next lecture we are going to see bivariate normal distribution.